All right, people, here we go. Jumping into unit 3 probability. Trying to go fast. We've seen a lot of this before, but good to review. Law of large numbers basically says this: as our sample size goes up, assuming no bias, our sample mean should approach the population mean. Or if we're talking about proportions, our sample proportion should approach the population proportion, or P. Cool. What it doesn't mean is the law of averages, which is, hey, things are going to even out, right? You hear it all the time if you watch the NBA or any sports event. So he does something wrong like 5 times in a row. They're like, oh, law of averages said he's going to make his next shot. All right. That's not true, right? That ball doesn't know it's supposed to go in because Steph Curry's missed 4 in a row. It just goes in because he's good, right? No, he still has a 40% chance every time he shoots. So one of the classic questions was this: you flip a coin 20 times, the first 10 end up being heads. What do you expect after you finish all 20? So your first 10 flips are heads, 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 10 in a row. Once you finish, how many should you have? Law of averages would say 10 and 10, but that's not true, right? Law of averages says that, but we know that in reality, if there's 10 more tosses, and that's a fair coin, we should have 5 heads and 5 tails. So in the end, we'll have 15 heads and 5 tails. Notice that that's the expectation. We are expecting to start approaching the true population proportion, which is 50%. We were at 100% heads. Now we're at 75% heads, right? Moving towards this. If we kept doing it 1,000 more flips, we should probably expect to get closer and closer to that 50%. Cool, cool. All right. And versus or. And means both must be true. And we denote it with this little thing like this. That means intersect. And then or means one or the other or both. Okay. In statistics and math, or means they could both be true. So we say that with this, which means union. Okie dokie. So when we see these things, this means and, this means or. Multiplication rule. This is, I believe, on your, we can derive it from your green sheet. I'll show you in a second. Probability of A and B is equal to the probability of A times the probability of B given that A has happened. So A has happened. That might change the probability of B. There's sometimes this happens. Here's an example of it. We have a pack of cards. What's the probability of 2 aces without replacement? So what's the probability I pull an ace on the first? That's 4 out of 52. 52 cards, 4 aces. But if I don't put that ace back in, there's now only 3 aces out of 51. So this is the probability of the first one being an ace. This is the probability of the second one being an ace, given that the first one was an ace. Okay, and we can multiply that out, find the probability. If they're independent events, the rule changes a little bit. Probability of A and B is equal to the probability of A times just the probability of B. Independence means that B happens at the same proportion or percentage no matter what A does. They're independent of each other. Okay. Example of this, probability of 2 aces with replacement. All right. So we pull an ace, 4 out of 52 chance, put that ace back in, shuffle it back up. What is our chance? 4 out of 52 again, right? Okie dokies. Let's see. Oh, I promised I would show you where to find this one. There's a probability section. So if you go where it says probability, you see this one right here. This is conditional probability, which we'll get to in a second. But if you multiply both sides by probability of B, you'd have probability of A and B is equal to probability of B times the probability of A given B, right? And we could flip that around with this being probability of A as well, and this being B given A, right? A and B is the same as B and A. Okay, so that is a place where you can go to get this one, even though it's not officially on this sheet. Cool. Addition rule formula also on there. Addition rule formula is right here. Okay, so we see addition there. Boom. Addition rule formula looks like this. Probability of A or B happening, that could be this, is probability of A happening plus the probability of B, hence addition rule, but we're going to take away the probability of the overlap. Oops, A and B. Okay, basically what we're saying here is we've got A, we've got B. If I add this to this, we end up counting this region twice, so we have to take it away once. Okay, so we're going to take away one of the overlaps, and that would give us the probability of this. Cool, cool. All right, independence. Two rules. This is your formula sheet, so just a little reminder. Formula. This is formula sheet-ish. You can derive it from your formula for conditional. All right, rules for independence. If two events are independent, probability of A given B is the same as the probability of A. Knowing B happened doesn't change this. If I said, what's the probability of a junior coming into my classroom? And I said, the person will have a pencil in their hand. Does that help you? Does that help you with the probability? No, right? Pencil in a hand is probably independent of of what grade level you're in. Although who knows? Seniors this time of year may not have anything, just traveling around with, I don't know, lacrosse sticks and stuff. All right, if independent, the other one is probability of A times the probability of B would equal the probability of both A and B. And I could use this instead of A if I want to. Okay, so that's another way to check. If 50% of the people in the school are male and 25% of them are seniors, 12.5% would be both if they're independent of each other. Okay, mutually exclusive. Two events can't happen at same time, right? Something is a cat and something, oh my gosh, I can't remember, and has wings. It's impossible. There's no cats with wings. Illegal, right? So being a cat and having wings, mutually exclusive events. Some of you are starting to go, well, what if you put zip it? All right, Venn diagram problems. At a breakfast buffet, there's 150 people. 93 chose coffee, 47 chose juice, 25 chose both, right? We're going to draw a nice big Venn diagram. Problem like that's kind of good. We can go coffee, we can go juice. We know there's 93 in this full circle. We know there's 47 in this full circle. We know there's 25 in the overlap. Okay, what I can do here is calculate what's coffee but not juice. That would be 68. What is juice but not coffee? So this little kind of like partial moon, is it a waning gibbous or a waxing gibbous? That's the question for you. Pause and discuss amongst yourselves. All right, good stuff. So a person chose coffee or juice. We can do this a couple different ways. You can do coffee plus juice minus the overlap would be one way to do it. The other way to do it would be just to add the gibbous with this little thing with the other gibbous, right? 68 plus 25 plus 22. So either way is going to get you the same number. You can check it out if you want. A person chose coffee and juice. That's easy. That's 25. That's right smack dab in the middle. Oh, it's asking for probability. Find the probability. So I got to put these over 150. Put that over 150. Person chose juice given that they chose coffee. So as soon as I see given that they chose coffee, that goes on the denominator. Okay, so how many people chose coffee? 93. Of those 93, of the 93, how many also chose juice? 25, right? So that would be the probability. Of the 93, 25 chose juice. Cool. This is conditional probability. This is on your formula sheet right there, right? Right there. Probability that somebody juice given coffee, right? Or sorry, coffee given juice, chose coffee given juice. So coffee given juice, probably of juice, probably of coffee and juice. Boom, that's exactly what we did. I don't even have to think about it. And it's really easy if you're working in tables or this to figure it out without that formula. All right, here we go. Two-way problems, two-way tables. Find a probably a randomly selected person wearing yellow and has blue eyes. So yellow and blue eyes wearing yellow and blue eyes, that's 10 out of the total, which is 62. Remember, this is not data here. These are the marginal totals. Find a probability of random person wearing yellow or has blue eyes. So there's 40 people wearing yellow. There are 12 people with blue eyes, but I have to subtract the overlap of 10. Okay. And that's going to be out of 62. Okay. The other thing I could do is add 30 plus 10 plus 2 and make that over there, right? I could add this, this, this. It's everybody but this. Find a probability wearing yellow, given that they have blue eyes. So we know they have blue eyes. How many people have blue eyes? There's 12 people that have blue eyes. So given that they have blue eyes, total blue eyes, right? How many of those 12 are wearing yellow? 10. Cool, cool. All right. Probability trees. Good way to solve some problems here. Conditional probability. 20% of prior students are left-handed. All right, so let's do this. So we're going to go 0.2 are lefties and 0.8 are righties. Good. Of the left-handed students, that's these, 70% love Justin Bieber, 0.7, and that means 0.3 do not love Justin Bieber. And then of the right-handed people, it's 50-50. So 0.5 and 0.5 love and don't love. Yeah, it's either one or the other. What percent of all prior students love the Biebs? Well, you can love him and be left-handed. You could love him and be right-handed. We need to multiply. 0.2 times 0.7 is 0.14. 0.8 times 0.5 is 0.4. So we're going to add those together. And that equals 0.54. 54% love the Biebs. Cool, cool. If I see a prior student with an I love Justin Bieber t-shirt, assuming this is truly how they feel, what is the probability that they are left-handed? Another conditional probability. So we know they love Justin Bieber. So that's going to go on the bottom. And of those people, that's these people and these people, which is the left-handed? Left-handed is there. So 14% of this 54% are that. And then I could figure out what that is if I want to, right? I probably put that into a decimal is a good idea. All right, random variables. I think we're cruising along fine. What do you think? All right, this is in your formula. Discrete random variable. When you see something like this, there's a probability of a whole bunch of different outcomes. That's a discrete table. So I'm looking here for discrete random variables, and I see it right here. Discrete random variables, right? And this is going to give you the formula. The formula for the mean of them is sum of the outcome times the probability of the outcome. Okay, so that means I take the outcome, this would be X, this would be probability of X, and I multiply it by this. That's going to be 0. 1 times 0.1, 0.1, 2, 0.2, 0.75, 2.0, right? So that's xi times pxi, right? That's what we're looking for. We're going to add those together, and that's going to give you the mean of them. So the mean of the x is going to be equal to, I believe it's 3.05. Something like that. It's pretty close. All right, the standard deviation also on the formula sheet. So I'm going to write formula here. It is on the formula sheet. Know where it is so you can use it. This is a trickier one, right? So it says we're going to take each outcome minus the mean and square it. And then we're going to multiply by the probability of that outcome. And then I'm going to sum them up, and then I'm going to square root them. Okay, so know how to use this, right? Know how to use this. You don't have to have it memorized, sitting right there. So the formula is going to be, for this one, the square root of, and I'm just going to start putting it in. It's going to be the outcome minus the mean. So 0 minus 3.05. We're going to square that and multiply it by the probability of that happening, 0.05. Then I'm going to add it to the next one. 1 minus the mean, 3.05. Square that, multiply it by the probability, 0.1. I'm going to keep doing that till I get to the end, which would be 4 minus 3.05. We're figuring out how far something is from the mean and squaring it. We do that a lot in stats, right? And then we're just multiplying by the probability of that happening. I don't know what that ends up being. I thought it was like 1 point something. You can figure it out if you want. Okay. On an exam, you could do this, plug it in your calculator. All right, linear transformations of random variables. So I have a random variable and I'm adding or multiplying or dividing, subtracting, right? So what does adding and subtracting do to everything? Think about a test, right? Let's say I give a test out of 20, but I'm turning that into a test out of 100. And I'm doing that by multiplying by 6 and then subtracting or adding 10, right? I'm giving you a linear adjustment. So I'm multiplying and adding. What is that going to do to the mean and the standard deviation, right? So if I add or subtract, think about this. If I had a regular old distribution and I add 5 to every point here, it would move up. Okay, does the center change? Yes, right? It moves up or down by the amount, right? If I add, it moves up. If I subtract, it moves down. Does it change the measure of spread? Is not going to change, right? Because the lowest and the highest are both moving up by 5. The range stays the same. Yeah, there's no change. No change. And this is true of any measure of spread. We could have standard deviation. We can have IQR. We can have range, right? And this goes for any measure of center. For us, it's usually mean and median are the two big ones that we talk about. Okay? Mode would be the same. All right, if we multiply and divide, though, if I go from 20 and I'm just multiplying, I multiply every score by 5, let's say, to get to 100, right? 1 to 20, but I multiply everything by 5. Now the distribution looks like this. It's going from 1 to 100, let's say. Let's say my low score is 1. Now it's 5. I got 0. 0 to 20, 0 to 100. What's happening? Is the center changing? Yes, right? Yes. It's going to go up or down, multiply or divide by the amount. So if we're multiplying by 5, the mean's going to multiply by 5, right? If we divide by 3, the median's going to divide by 3. Measures of spread, are those going to change? Yes. Yes, they are. They're going to multiply or divide by the amount. Cool? Cool. Let's see. I think we're good there. Yeah. Mr. Rebuff gives a test out of 40 points. He applies linear transformation, blah, 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 where X is the original score out of 40 and S is the final score out of 100 that he puts in the gradebook. If the mean and standard deviation of the original test were 32 and 4, what are the transformed? All right, so the transformed mean, after I multiply every score that I get by 2 and then add 20, the mean is going to be affected by both of these, right? So we're going to go 2 times 32. The multiplication affects it. And so does the adding of 20. That's going to affect it as well. I think the new average score is going to be 84 out of 100. So it was 32 out of 40. Now it's 84 out of 100. The standard deviation with this linear transformation, only the multiplication is going to affect it. So we're just going to go 2 times 4. Standard deviation is 8 points. That's it. Easy peasy. Easy as pie, y'all. Yeah, cool. Cool. All right. Dang, are we almost there? 2 pages left. How much time do I got? Ooh, 7 minutes. I don't think I'm gonna make it. We'll find out. Mr. and Mrs. Reeboff are splitting a marathon. I run with 135 minutes and a standard deviation of 5. Mrs. Reeboff is 105 with a standard deviation of 10. If we assume independence between the times, which we could talk about that, what would the mean and standard deviation of their combined marathon? So the mean of Mr. plus Mrs. time, if we're combining them together, would just be, we're going to add their times together. Mr. Rebuff usually goes 135. Mrs. Rebuff usually goes that. That's 240 minutes. Okay. Standard deviation, though, of Mr. plus Mrs., we can't add standard deviations. We got to turn them into variances, and then we got to turn them back. Okay. So Mr. Rebuff's is 5, so his variance is 25. Mrs. Rebuff's is 10, so her variance is 100. But then to that, so that's the combined variance. To get it back into standard deviations, we got to square root it. I believe, I could be wrong. I think that's, oh no, not on the formula sheet. I don't believe. Okay, you just got to know that. Okay. Again, assuming it depends, what is the mean and standard deviation? The difference of their times, Mrs. minus Mr. So on average, how much does Mrs. Rebuff beat Mr. Rebuff by? So 135 minus 105. So we would subtract those. She beats him by an average of 30 minutes. Okay. She's at the finish line waiting for me with a slice of orange because she's so nice. Mrs. minus Mr. equals standard deviation. Guess what? It's exactly the same. We always add. Okay. Always add. We could talk about in class why. We're just going to do the notes there. It's always adding. All right. Binomial and geometric random variables. Check your bins, of course. And then understanding the formula. This is on your formula sheet. We're talking binomial. So let's look for binomial. There it is, binomial distribution. There's the binomial formula right there. So that's what we're going to look at. That's what we're going to look at. Oh, man, I got so close. This is called n choose k. It's not n divided by k. That's very important to know. We're not dividing these two. Okay, this is basically how many ways can this happen? Okay, so let's say I shoot 4 free throws and I want to know how many times I can make 4, right? So 4 choose 3. This is shoot 4 free throws, make 3. That can happen 4 different ways, right? I can make, miss. I can make, miss, make. I can make, miss, make. I can miss, make. There's 4 ways. So 4 choose 3 or, yeah, 4 choose 3 is equal to 4 because there's 4 different ways that that can happen. Okay, so that's what n choose k does. We'll show you how to use your calculator to find that. I don't know if I put it down anywhere. To do this on your calculator, I believe you go math, PRB, and you're going to put the number in first. So you're going to put the number, let's say if you were doing 4, 3, you would do 4, and then go math probability to find NCR, and then you would put in 3. So that's what it would look like. So 4 choose 3. I shouldn't have had that little line there. Sorry. Such a habit. 4 choose 3 would be 4 NCR 3. Okay? And that's what that is. P here is your probability of success, right? 1 minus P is your probability of failure, right? K is your number of successes. N minus K would be your number of failures. Okay. It's important to know how to use this formula. You're probably not going to have to use it by hand, but man, I can almost guarantee you a multiple choice problem that'll have 5 of these and it'll say which one is Mr. Reebok shoots 4 free throws and makes 3 out of them, the probability of that. And they'll give you this, right? All right. So Mr. Reebok makes 90% of his serves in volleyball. What is the probability he makes exactly 3 out of 4 in a set? Okay, so if I was using up above here, that would be 4, choose 3, right? My probability of success is 0.9, and I'm having 3 successes. My probability of failure is 0.1, and I'm having 1 failure. Okay, this equals 4. Again, I'm going to go to NCR. I could do something like this to figure it out, or I can go 4 NCR 3 and figure out what that probability is. Okay, we would probably use our calculator if we're given this problem, and we would go binomial CDF, or sorry, PDF, because it's exactly one outcome. So binomial PDF because it's one outcome. Okay, we'll talk about CDF in a second. And I think I plug in the number of trials, the probability of success, and then the number of successes, and that's going to spit out a number. Okay, so that's that. In last Saturday's tournament, he served 32 times. Why is there a question mark there? Of course I did. What has probably made 25 or more? So 25. Here's what Mr. Rebuff does, 26, all the way to 32. So I want to know the probability of this, right? Some calculators will let you do that. right, will let you go, hey, what's the lowest? What's the highest? A lot of calculators, you're going to have to use a little trick. When it's more than or at least or something like that, 1 minus binomial CDF this time because I'm accumulating. We're accumulating. And then I'm going to go, there's 32. Probability of success is 0.9. And I want to get rid of, this is the get rid of part. I want to get rid of 24 and below. So I'm going to put 24 here. Okay. If I do that, if I get rid of all the probability of 24 and below, I'd be left with a probability of 25 and above. Make sense? So use minus when it's or more, or at least, or something like that when it's going to the higher things. Some calculators can handle it without that, so you're fine. Okay. Find the expected number mean and standard deviation. So that is right here. Binomial mean, standard deviation. They've got the formulas for it. Super easy. It's right there. Okay. So this is formula. And formula is the mean is going to be of makes, if I serve 32 times and I make 90% of them, that's going to be 28 or something like that, 29, right? The standard deviation, again, I'm going to standard deviation of this is square root of n times p times 1 minus p. N times p times 1 minus p, right? Successes, probably success, probably failure, boom. You can figure out what that is. Cool. Yeah, that's it. That's it. That's it. Oh my gosh. My gosh, I'm a little over. Can I finish? Can I finish? I think so. Let's just go for it. All right. Difference between geometric and binomial. This is a fixed trial size. Take 10 free throws in a basketball game. Geometric is how many trials till first success. How many 3-pointers do I shoot until I make the first one? That's geometric. All right, all right, all right. Oh, I left my pen where I went. Ah, we'll grab something here. All right. Where are we at? Share. Camera. Switch camera. Please work. No, not that camera. There we go. Oh my gosh. I thought I was gonna have to turn it off. We're good. We're good. We're good. Here we go. Understanding this formula. Again, this is on the formula sheet. We are now in geometric land, right? So you're going to go to your green sheet, make sure you know where this is. It says geometric right there, gives you the geometric formula. And then this one here, you hardly ever use this one. Never seen it be used. But that one you can see. So, I mean, if they gave you that one, it's on the stuff, so you could do it. All right, so here we go. Probably the x equals x. Okay, so first success is on the X try. Okay. This is failure. This will be number of failures. So number of fails. This is success. And we're going to tell our first success, we only have one success, right? Pretty easy formula, right? Mr. Reboff makes 90% of his serves in volleyball. Was probably at his first miss. So the probability of a miss is equal to 0.1, right? Is his third attempt. So what does that mean? That means that I am missing my first two. So 1 minus point, oh, sorry, my first miss. That means I make, and then miss. Sorry. So 1 minus 0.1 has happened twice, right? Failing. In this case, a success is a miss, right? So my first success is the first miss. It's weird, right? And then 0.1 to the first power. right? If I'm using geometric PDF, that's if I use the formula, probably the x is equal to 3, right? Or big X equals 3 equals that, right? If I'm using my calculator, it's just geometric PDF because it's exactly the third time, right? So one outcome. Geometric PDF, and then I think it's P and then X, right? So I believe it's 0.1 comma 3. Okay, either way, it's going to spit out the same thing. Okie dokie. All right. First miss is before my fifth attempt. That means my first miss is on the first or second or third or fourth attempt. The fifth and beyond we don't want, right? So we're going to do geometric CDF because we're accumulating, right? Adding. It's not just one of these, it's multiple of them. And we're going to go 0.1 comma 4. This is 4 or less, right? That's what I want the probability of. All right. Mean or expected value of geometric. What is the expected number Sirs to get his first miss? Okay. So again, I'm going to grab my formula sheet, and that's just going to be right here, right? Mean geometric 1 over P. So expected is 1 over 0.1, which is 10, which kind of should make sense. If I miss 10% of them, it would take about 10 on average to get my first miss, right? Right. There we go. We did it. Yay. See y'all, people.